Hello, AP Stat students. Today we begin Unit 2, which is displaying and describing two variable data. In Unit 1, we displayed and described situations where we had one variable, either categorical or quantitative, and we learned how to describe that one variable in either situation. Unit 2, we're going to be looking at what happens when you have two categorical variables you want to look at together, or two quantitative variables that you want to look at together. So Unit 2, two variables, okay? And we're going to start off by displaying and describing two categorical variables. So situations like, is there a relationship between gender and eye color in AP Statistics students at Jefferson High School in 2020? Recall that we had you fill out a survey where you told us your gender and your eye color. And we're now going to look at that data and see what we can learn about gender and eye color in AP Stat students at Jefferson. Okay, so when comparing two categorical variables, we would like to know if there's an association or relationship between the two variables. Okay, independent means that the categorical variables do not have an association, so there's no connection between them. And dependent means that the categorical variables do have an association. So for instance, variables that are dependent would mean like males might be more likely to have a certain eye color and females might be more likely to have a different eye color. Okay, so that's what we're looking for. If male or female does not determine your eye color in any way, then we'd say that they are independent. Okay, so that's what we're trying to do. Below are the results of a survey given to all AP Stat students. The results have been shared in what's called a two-way table right here. It's also called a contingency table. Okay, that's called both things. We put the variable eye color across the top and the variable gender down the sides. Okay, and then there's also a total row, so the totals for each eye color, and there's a total column, which gives you the totals for the genders. Okay, so that's what we would do, is make a table like that, and basically you would just count up, how many males had brown eyes in our data, and write those in the table, etc. Okay. Then the first thing we will look at is called a marginal distribution, and it's just a frequency or relative frequency distribution of either the row and or a column variable in a contingency table. Okay, to find the marginal distribution, you take the row and column totals in a two-way table and divide by the total for the entire table. Okay, so if you look at the chart above, change colors to highlight this. So we'd figured out the marginal distribution of each eye color. Okay, and the way we do that is we take, like for instance brown, we take that there are 63 people with brown eyes and we divide them by the table total of 157 people, and we get 0.40. That means 40% of the people in AP Stats have brown eyes. Okay. And then we do the same for gray eyes. There were 5 people with gray eyes out of 157, gives us 3%. So you can see gray eyes is much smaller than brown eyes in AP Stat students. You can see if we continue, we had 13% hazel, 36% blue eyes, and 8% green eyes. So that's the marginal distribution for eye colors. We can also do the marginal distribution for gender in our table, where we take the total for the males, 66, and divide it by the total for the table, 157. Gives us 42% of the AP Stat students were male, or are male. And then we do the same for the females. We have 91 out of 157, gives us 58% of the AP Stat students this year are females. Okay. So back to the notes. It says marginal distributions give big picture information about the variables collected. So you can see now that there's a much higher percentage of females in AP Stats than there are males. That's very interesting. And you can see that brown and blue eyes dominate the eye colors. So we can see that the marginal distribution of gender, there are 16% more females taking AP Stats than males. We can see from the marginal distribution of eye colors that brown and blue are by far the most common eye colors of students in AP Stats, where gray, green, and hazel colors make up a very small percentage. Remember, marginal distributions give us big picture information about the variables collected. but they do not tell us much about how the two variables are related to each other. Okay, and that's always more interesting, okay, to see how the two variables are related. So for that, we need a different distribution. And that we call the conditional distribution. So a conditional distribution is a relative frequency distribution for a subset of the data. Okay, so a conditional relative frequency is a relative frequency for a specific part of the contingency table. Example, the cell frequencies in a row divided by the total for that row. Okay, so we're going to be looking at focusing on one variable, either eye color or gender, and seeing the distribution of the other variable within that. So there are two conditional distributions we can compute in this contingency table. We can do the conditional distribution of eye color by gender, or we can do the conditional distribution of gender by eye color. Okay, and both give us interesting information. So we will first find the conditional distribution of eye color by gender. In this instance, we will look at each gender separately. Okay, this is important, each gender separately, and compute the probability of each eye color within that gender. Okay, so notice for the males, we did that right here, we looked at just the male row of the table. Okay, and there were 66 males altogether, so we took every eye color and divided it by 66, which we did here. Okay, so basically we figured out what percentage of the males had brown eyes, what percent had gray, what percent had hazel, what percent had blue, what percent had green. And what we usually do with those numbers is we put them in the table in parentheses. So you can see in that first box of the table, males with brown eyes made up 48%. So of the males, 48% of them had brown eyes. Of the males, 3% had gray, 17% had hazel, 27% had blue, and 5% had green. So you can see for the males, the brown eye color dominated our AP Stat students. Almost half of the males had brown eyes. Then we do the same thing for the females. So over here I took the females, and there were 91 females, so I divided all the eye color numbers by 91. So this time we're looking at the female row. So we're locked in on only that row. So we did like 31 out of 90, 91 is 34%. So I put that in the table in parentheses next to in the brown female group. So you can see for the females, 34% had brown eyes, and 3% had gray, 11% had hazel, 42% had blue, and 10% had green. So notice for the females, their highest percentage was blue eyes, okay? Where for the males, their highest percentage was brown, okay? So that tells us right away that eye color and gender are actually going to be dependent, okay? Because if you're a male, you're more likely to have brown eyes. If you're a female, you're more likely to have blue, okay? So these two variables are related to each other. So we can tell from this conditional distribution that males are more likely to have brown eyes and females are more likely to have blue eyes. Because of these facts, we say that eye color and gender are dependent. If males and females had the same percentage of eye color, like gray eyes in the table, where they each had 3%, for each eye color, we would say that eye color and gender are independent. Okay, so it's pretty easy to tell independence and dependence from a table. We're just looking at comparing these numbers that I'm circling in red, and if they're about the same for each eye color, then we'd say the variables are independent. If they are different for each eye color inside the genders, then we say they are dependent, okay? At the bottom here, another way to check for dependence is to see if the marginal distribution matches the conditional distribution, okay? So I wrote in the marginal distributions here for the table, and if they're independent, we should see that percentage carry forward throughout the table. So we should see that 40% of the females had brown eyes and 40% of the males had brown eyes, if they were independent. Same thing here. Now notice for gray eyes, the marginal and the conditionals do match. So if they had matched across the board, we would say they're independent. Okay, but you can see that none of the rest really match. Now, we could find the distribution, or the conditional distribution of gender by eye color. Okay, so this time we look at the eye colors separately. So I did the brown eyes first. There were 63 people with brown eyes, 32 were males, 31 were females. The split was 51-49%. And I did the same thing for gray, same thing for hazel, blue, and green. So this time we're looking this way on the table, at each eye color separately. Okay. And, excuse me, this distribution also shows us that eye color and gender are dependent. Okay? The marginal distribution of gender is not true for all the different eye colors. So if they were independent, 42% of the table was males, so 42% of the brown eye people should be males, 42% of the green eye people should be males, etc., etc. And that's not the case. Okay? You don't need to make both conditional distributions for a table. We usually just pick one and compute it. And I think like in this case, it was more interesting to see the male makeup of eye color and the female makeup of eye color in the previous slide. So doing the eye color by gender, I think, was more interesting. Now, there are two graphs that can be made for conditional distributions. A segmented bar graph and a side-by-side bar graph. Okay, so we're going to do the distribution of eye color by gender. Okay, so we looked at the table this way. Like out of the males, what percent had each eye color, and then out of the females, which gender, or which the makeup of the eye colors for the females. So in a segmented bar graph, what we do is we make a bar for the males and a bar for the females. You can see here, there's one already made. We scale the y-axis from 0 to 100%, because if you notice, if you add up all the percentages for the males, they add up to 100%, and if you add up all the percentages for the females, they add up to 100%. And then we make a bar that goes to the top, and we divide it up amongst the eye colors. And you'll always want to have a key when you do this. And if you were doing this by hand, instead of using colors, you could do things like, you could say that the blank part will be green. And you could say that I'm going to make dashed lines for blue. And you could say I'm going to make fill it in for hazel. So you could make this with like a pencil and just do different patterns inside each part. But then notice, like I'll just show a couple examples here. For male brown eyes, it's supposed to be 48% here in the table. So down here, the male brown-eyed section is 48%. It's just under 50 if you look. And then I just keep stacking it up. So the gray eyes were 3%, so you can see there's 3% in there. Then hazel is 17. You can see each part corresponds to its percentage in the table. Okay. If you look carefully at these two graphs, you'll notice that the colors do not match up. Okay. The blue is much bigger for the males than it was for the females in the picture. Oops, sorry, females is spelled wrong. When that's the case, when the graphs don't match up, that's another way to determine that they are dependent variables. Another type of graph is called the side-by-side bar graph. And that is simply, instead of stacking the bars, you put them next to each other. Okay. So notice this time, I only have to scale the y-axis to 50% because the biggest group that was in the table was the male brown at 48%. So that's as high as I need to take care of, so I missed to make it to 50. And then you'll notice instead of stacking the bars, we just do a separate bar for each eye color. Again, these are called side-by-side bar graphs. And again, if you look at them, you'll notice that they have different shapes. Okay, like the blue bar is higher for the males than it is for the females. That's another piece of evidence that these variables are dependent, okay? If they were independent, those two side-by-side bar graphs should look almost identical. So here's another example so that you can understand this. When you're interpreting categorical variables, you want to make a graph of some kind, so either the segmented bar graph or the side-by-side. I would probably recommend the segmented. I think it's probably easier to read. You want to give evidence from the graph, and you want to mention a couple categories for each variable if you're comparing them. Okay. And remember, dependent means there's an association between the two variables, and independent means there's no association. So here's a table of information. They did a survey at a company, and they asked people their level of smoking, so none, light, medium, or heavy smokers, and then they asked them what kind of employee they were at the company, either senior manager, junior manager, senior employee, junior employee, secretary, etc. So you can see from the table, we've got all the numbers. So we decided to create a segmented bar graph to show this data. So you can see we did smoking levels by management type or employee type. So you have your 5 types of employees, and then we have a bar representing each level of smoking, and your key is over here. Okay, so right away you can tell these variables are dependent. The graphs do not line up. Okay, you can see that the heavy smoking is the green, and you can see that the junior managers are the heaviest smokers, where the senior employees are have the least heavy smokers. And if you look at the blue, the people that don't smoke at all, you'll see that the senior employees, or almost half of them, don't smoke. But for the junior employees and the junior managers, less than 25% don't smoke. Okay. So if I was describing the relationship between these, I would say that junior managers and junior employees are more likely to be smokers at this company, and senior employees and senior managers and secretaries are the least likely to be smokers. At the bottom here, this is what the graphs would have looked like if these two variables were independent. Okay, so notice that all the graphs basically line up. So when all the graphs basically line up, that's when they're independent. Okay, this is just an example of what independence would look like. And then here's one more example. In this table, you can see they looked at people's employee records, and the top variable is your minority classification, so either yes or no. And then on the side was what kind of job do you have? Are you clerical, custodial, or a manager? Okay. And they looked at minority classification by management type or employment category, okay? And they made segmented bar graphs. So if you look at them, you'll see that using the key, in the management section, almost all of the managers are non-minority, okay? But if you look at the custodial and clerical, the minority group makes up a bigger chunk of those groups than it does in the management groups. So that shows us that these two variables are dependent, okay? You're much more likely to be a manager if you are not a minority, okay? The bottom graph shows an example of what this graph would have looked like if they were independent, okay? If they're independent, you'd see it doesn't matter which group you're in, your chance of being non-minority is the same, and your chance of being in the minority group is the same, okay? So if the graphs line up, they're independent. If they don't line up, we say the two variables are dependent.